Hello, everyone. Welcome to Differential Calculus. I wanted to start each week by kind of giving a little bit of historical context and giving credit to where credit is due, the historical figures that kind of motivated the ideas that we're going to be talking about for the week. So to begin here, we're going to talk about a guy named Zeno of Elea. And he was a Greek philosopher, famous for asking questions, famous for asking provocative questions. The Greek mathematics at the time, Zeno sort of had a problem with. He said the mathematics was very finite, and there are processes in the actual world that are incompatible with the mathematics at the time. He was famous for sort of giving riddles to people. He was a part of a school of Parmenides, Parmenides is a famous philosopher at the time, and he believed that he should trust logic, or everybody should trust logic over their own senses. He was very distrustful of pretty much himself and perceptions of the world, and he trusted logic more than that. And Zeno, as his student, one of his prodigy students, thought the same thing, and he was trying to show everybody that really we should be trusting logical conclusions more than what we see, smell, feel, touch, things like that. And one of the things he really pointed out was that the mathematics at the time was absolutely insufficient, and he did so by giving paradoxes. He introduced paradoxes to challenge human assumptions. In particular, I'll show an example of a certain paradox. By the way, this is, I got some photos, of course, online. This is Zeno. That's a drawing of Zeno. And these are some Elean ruins. So Elea was a Greek city 500 years before Christ. And I don't know, I just found some photos here that I thought were kind of cool. But anyways, this guy Zeno, what did he do? What did he pose? Why did he think there was a problem? Well, one of his famous sort of riddles is called Achilles and the Tortoise. Let's see what it says. He said, let's suppose that we have Achilles, who is an athlete, a soldier, wants to race a turtle. And of course, Achilles thinks that he's going to be able to completely beat the turtle easily, steadily. So what Achilles does is he allows the turtle to get a head start. So he says, go ahead, and I'll catch up to you. Or so he thought. So Achilles allows the turtle to get here. So let me kind of draw a future turtle. Turtles are hard to draw, guys. You guys get the idea. And what Zeno was saying is, there's a problem here. He argued that Achilles will actually never be able to reach the turtle. Even though that completely defies logic, we can imagine Achilles beating the turtle, but that's what Zeno was saying. He was saying that, I don't think we can trust our senses. I don't think it actually happened because I trust the logic that I'm about to pose more than what I'm actually seeing in the race. So what Zeno says is he allows the turtle to get a bit of a head start, and then Achilles tries to catch up. So here's Achilles catching up. And Achilles catches up. But this is where the problem is. During that time that Achilles was running up to the turtle, it's not like the turtle stopped moving. So during that time, really what Achilles caught up to was where the turtle was when he started running. So during that time, the turtle made another advancement. Oh, let me try that again. Maybe something like that. So Achilles catches up to the turtle. Or, excuse me, he doesn't catch up to the turtle. He catches up to where the turtle was when he began running. And when he gets there, he goes, oh, shoot, the turtle got a little far ahead of me. Oh, that's okay. And then he tries catching up to the turtle again. You guys are going to get the paradox pretty quickly. And then, of course, again, Achilles gets to where the turtle simply was when he had to make that advanced step But during that time, of course, the turtle made another advancement. So when Achilles gets here, the turtle was not still there. It had already advanced here. Right? So here's the turtle. Zeno's saying, yeah, this is a problem. I don't think Achilles ever makes it to the turtle. I don't care what I'm seeing happening. I'm saying logically that can't happen. So this turtle keeps slightly jumping ahead of Achilles. And Achilles, frantically, thinking he's a hot shot, is recognizing that he can never catch up to the turtle. And I'm tempted to say the turtle wins. That's not necessarily what I'm saying. What I'm saying is Achilles never catches up to the turtle. Every single time Achilles tries to make an advancement, during that time, the turtle also spends time making its own advancement. It's impossible for Achilles, again, these are Zeno's words, impossible for Achilles to ever catch the turtle. So he says this to a crowd of people in Greece, and everybody starts freaking out. They start looking at their hands, not thinking that reality is real. And Zeno's just kind of smugly sitting there going, yeah, I know, you shouldn't trust what you see, because I'm pretty sure that you can never, catch up to somebody, is pretty much what he's saying. In fact, Zeno doubled down, and he says, not only do I think that Achilles can never catch up to the turtle, I don't think anybody can ever cross a finite distance, because in order to cross a finite distance, you have to complete infinitely many steps. If I want to go 1 meter, put simply, if I want to go 1 meter, I have to first go half a meter, and then I have to go 3/4 of a meter, and then I have to go, 7/8 of a meter. And then I have this much left, but I still have to first accomplish half of that. And then I have this much left, but I first have to accomplish half of that. And therefore, you can never actually reach the meter. So the big claim of Zeno, and I can be kind of like corny is in a way, because let's say we're 7 minutes into this video, and what you guys had to do, so here, you're on YouTube. I've trapped you all inside of an infinite loop of watching my video, mwahaha. You guys first have to watch half of my video of this video. And then you have to watch 3/4 of this video. Your next goal is to watch 3/4 of the video. Oh, shoot, but then you have to watch, 7/8 of this video. And this process continues, which means that once you started this video, you can never finish. I don't care what your perception says. Again, I'm talking as if I'm Zeno. I don't care what you think is going to happen. You intuitively think that you can finish the video, but me as Zeno thinks that no, that's just a figment of your imagination. You are going to be trapped watching this video for eternity. Which also means I'm not going to get a view, which is kind of a bummer. I guess if you see the view count go up, that Zeno is contradicted. But anyways. So this was the big problem that Zeno posed. He said this world of mathematics has a problem, how we have it. And he offered no solution. He just said, yeah, I'm going to let everybody sit on this. What he showed was that the existing ideas were not good enough. Quite savage. Okay, to find our first answerer, the first person to really kind of take what he was saying seriously, and I guess he wasn't taking what he was saying seriously. Zeno was more of a philosopher, but he pointed out a problem in mathematics. This problem has sufficiently been answered in the mathematical realm, but philosophers to this day still struggle with a lot of Zeno's paradoxes. Here, let me zoom out so we can see everything. Including this famous one of Achilles and the tortoise. There are many others. I encourage you guys to look up Zeno's paradoxes. But to get our first sufficient mathematical answerer, we have to go about 200 years later to a man named Archimedes of Syracuse. This was fun to kind of look up pictures and stuff of these mathematicians. So let me frame this right. And that looks good to me. All right, so Archimedes of Syracuse, I would argue is probably one of the greatest mathematicians of all time. It's hard to think of a mathematician that was able to think like him. People quote or they attribute Archimedes' mind as one of the best minds to ever exist. And I tend to agree. This guy was just beyond genius. Every single breath of his life he was just speaking creativity and mathematical genius to the world. And looking up at his inventions and how he thought is very, very inspiring. And also humbling. Like you look at what this guy was able to come up with, and you're like, oh man, there's no shot I'm going to come up with something like that. But I don't know. Choose to rather be inspired by it. So Archimedes was a mathematician in Syracuse. He lived from apparently 287 to 212 BC. Syracuse is in Sicily. And he lived in a time where Rome was slowly kind of taking over the world, and this was sort of like close to the end of the Greek, or the time where Greece was prominent and one of the larger countries or of the time, I guess. And but this guy's attributions to the world, contributions to the world are like super vast in number. He was, like I said, he's certainly top 5 mathematician of all time. He might be my favorite mathematician of all time. He's wildly focused, imaginative, and he's famously absent-minded. So he's kind of like one of those people. We all have that friend that's like always daydreaming and like kind of lost in their own world. I am unfortunately that friend in my friend group. I'm always kind of lost in thought, but certainly not as deep of thought as Archimedes. This dude was able to come up with insane things. He was dedicated to discovering truth in the world around him. I have sort of pictures of some of his famous inventions. This one's crazy. The claw of Archimedes. He invented this thing that was able to grab Roman ships and spill all of the sailors into the ocean before they actually met the shore of Syracuse. He famously came up with the law of the lever, which says something like the weight of an object times the distance from the fulcrum of the object. If the sort of seesaw or the fulcrum is in equilibrium, this has to equal the weight of the second object times the distance from the fulcrum of the second object. This is genius, and this is, of course, still used today. Those of you that are physicists, you will study this a lot when you study something called torque. Archimedes famously said, yeah, I believe in this law of the lever so much that if you give me a lever long enough and a fulcrum on which to place it, I can move the world. And that's because the weight of the world here can be compensated with a long enough distance. Archimedes won't have to push that hard as long as this distance is long enough and this distance is short enough. These two things have to be equal. So that was the idea in his argument. So that's the law of the lever. I got to speed up. I'm already 13 minutes in. Other inventions here, Archimedean screw. You can kind of see how it works just from this picture I found. It's pretty cool. And a whole bunch of war machines to help defend Syracuse from the Roman Republic at the time. Unfortunately, despite Archimedes' efforts, though, Rome got to him. This is a famous painting right here. Rome got to him as he was probably in his mid-70s. I think that this was one of the raids, during one of the raids of the Roman Republic. I think it was General Marcus Marcellus or something like this, said he knew of Archimedes. Archimedes was worldwide famous. Again, the world back then was a lot smaller than it is now, but Archimedes was worldwide famous for his genius ideas and his contributions to the world, that the Roman general, Marcus Marcellus, said, yeah, if you ever find this guy named Archimedes, make sure you don't kill him. We need him on our side. We want him to continue with his ingenious inventions. And so he told this Roman soldier to go get him. Roman soldier goes up to Archimedes, or finds Archimedes. In this picture, it's depicted he's in like a room or something. I think he was actually, it's true, he was actually on a beach and drawing circles and geometric diagrams in the sand in one of his super focused dazes in trying to discover mathematics. And the soldier says, "Hey, yo, you, Archimedes, apparently you're really valuable, so you got to come with me." No answer from Archimedes. He's deep in thought. Soldier gets perturbed and walks closer to him, and he walks through all of Archimedes' circles and diagrams in the sand, and that wakes Archimedes up from his mathematical trance and goes, and Archimedes famously says, "Do not disturb my circles." This is people actually quote him saying that. Don't mess with the circles. Don't mess with the circles. And the Roman soldier's all pissed and says, "I don't care about the circles. I need you to come with me. My boss, Marcellus, needs you." And Archimedes ignores him. He's so angry, and he's probably trying to reconstruct the circles as the soldier sitting there. Soldier gets super pissed. "Let's go, old man." Archimedes ignores him. Soldier says, "Enough with this," and smites him right there. Archimedes was like mid-70s when he died. Quite heartbreaking, but I guess he's a real one, really doing mathematics till his last breath. And, careless Roman soldiers, come on now. Like, he could have done something for you. But anyways, so how did Archimedes respond to Zeno in particular? That was a big trance. I could talk about Archimedes for forever, but how did Archimedes respond to Zeno in particular? This idea that infinite processes can't ever finish. Archimedes says, that's kind of an interesting idea. We're getting closer and closer through an infinite process to some sort of finite value. Archimedes thinks to himself, I can use something like that to figure out the exact ratio of a circle's circumference to its diameter. Those of you that are mathematicians know exactly what I'm talking about. Archimedes says, hey, I can approximate pi with your idea. Thanks, Zeno. So what Archimedes does is he grabs a circle, and let's also say the circle has diameter 1. So here, let me not draw that in the circle. The circle has diameter 1, and therefore the yellow distance, well, let's just say he's trying to discover the yellow distance. Those of you that are mathematicians and that are following along should think to yourself, oh, I know what that yellow distance is. So let's just say 1. I'm not sure the Greek units at the time, so I don't know, meters, feet, who cares? I'm just going to call it 1. We're mathematicians here, not engineers. So we're talking about a circle of diameter 1, and we want to figure out the distance or the length of this yellow arc here. If I were to lay a string around this circle and then lay it out, I want to know exactly how much that string is. This was unknown at the time. Well, other people approximated it, including famous mathematicians like Eudoxus. And I'm pretty sure Euclid did as well. Don't quote me on that. But nobody did it as well as Archimedes. What Archimedes did is he began with putting he did something like this. He began with saying, I can put this circle inside of a square. I wonder if I could do this. I'm not going to make this complicated. Forgive me for my picture. It might not be perfect. So he puts the circle inside of a square and says, I think I know at least the perimeter of this square. And so he says the perimeter of the square, obviously the base length and the height length are both 1. And so I think what he says is the yellow distance, I'm just going to call it yellow scribble, has to be less than the perimeter of the square, which is, of course, 1 plus 1 plus 1 plus 1. That's also known as 4. And he says, okay, so we have some sort of upper bound on this yellow length. And he said, well, it's not that accurate. So what I'm going to do is I'm going to rewrite this or redo this bound. So instead of the whole distance, he chops this part of the length off and this part of the length off and creates a new polynomial that is circumscribing the circle. Fancy word. Who cares what it means? You get the idea based on the picture. Okay, that's not supposed to across the actual yellow length. But again, this part is cut off, and this part is cut off. This part is cut off, and this part is cut off. Yada, yada, yada. That makes it look so bad, though. I don't know. I'll just do it for one. Okay, and then he has a more accurate description or approximation for the circle. For the yellow length, rather. Again, those of you playing along should know what that yellow length is. So this would be some number less than 4. I don't know. And then he keeps going. This process keeps going. And he keeps making smaller and smaller and smaller polygons that circumscribe the circle. All polygons that he can compute the length of, or excuse me, the perimeter of. And this is an infinite process. This is a response to Zeno. He's saying, hey, I'm using this infinite process. But then he says, but I'm going to argue that I can reach something, or at least I can't, maybe not reach something, but I can trap the destination. I might never reach the destination, but I can trap it. Here's what I mean, and here's what Archimedes said, is he said, you know what? This process is going to go on infinitely, but that doesn't mean it's going to go to 0 or something like that, because I think it's trapped from below. There's infinitely many processes to this, or steps to this process, but I think the process can't go further than this length. I'm talking kind of hoopla here, but you get the idea. He inscribed a square. Or here, excuse me. Inscribed a square. This is certainly much easier to find the... This is really the idea of what Archimedes did. I don't think Archimedes used a square. I think he started with a hexagon, but it's the same idea. I think we're about to get to a hexagon. No, we're not. Oh, we already did a hex. No, that's an octagon. Anyways, you can do some quick math to figure out this distance right here. And I think it's going to be root 2 over 2. 1 over root 2. Same thing. So 4 times 1 over root 2 for this first bound right here. He said that yellow length is, more than 4 times 1 over root 2, 2 root 2. Let me use a different color entirely. The more I do that, it's just going to make this video longer. I got to be... thanks for joining me on my time management lessons. We're almost done. So we have this blue length this time, and that's going to be 2 root 2. And he says the yellow length of the circle has to be more than that blue length. This is what he's saying. Archimedes is saying, I don't necessarily need to reach the destination of an infinite process, but I can trap the destination of an infinite process. This yellow thing is the destination. The infinite process is us circumscribing and inscribing larger and larger sided polygons. So this was the first step. And of course, maybe you can see in the picture what the next step he did. It looks something like this. And we're not going to spend time actually trying to figure this out. You can do it for homework. Kind of makes me wonder how one would do this. I mean, or how in particular Archimedes would do this. So you can't use calculus. Whatever calculus is, that's what we're doing. I like the picture. It looks good. Very pretty. Proud of myself on that one. But anyways, so this process keeps going. I'll give like a ... The process, or the actual length, the yellow length, is trapped, and Archimedes famously showed that at the end, this yellow length was bounded above by, a lot of us know this one, 22 over 7, and bounded below by the number, I have it here on paper, 223 divided by 71. And that's kind of meaningless. We have just fractions here, so let me give the decimal approximations. 3.140845 ... is less than this famous yellow number, and I'll go ahead and spoil it for everybody. This number is called pi. and pi must be less than 22 over 7 is approximately 3.142857. And those of us that know a decimal approximation for pi know that that's pretty darn accurate. Whatever Archimedes just did, let's see, it's accurate up to, I think that's 1/1000th of a decimal place. Anyways, so Archimedes did use this idea from Zeno to get a really good, accurate representation for pi. Let's see if I can finish this in less than half an hour. Jeez. So, to summarize, famous mathematician that really kind of started this idea. Oh, this process, last thing I'll say before I finish off. This is called the method of exhaustion. And I'm going to call it really the spark of calculus. This is really the inspiration for some of the ideas that later mathematicians such as Newton and Leibniz, Cauchy, Weierstrass, all people we're going to talk about in this class through these history videos, are really going to use. So this idea is mostly attributed to this guy named Archimedes. Archimedes really attributed it to this guy, Eudoxus, but Archimedes went with it. He took it everywhere. Eudoxus is first, like kind of between, he's kind of between Zeno and Archimedes in terms of dates, and he did this method of exhaustion before him, but Archimedes took it and ran. So to summarize, how does calculus begin? I would say that Zeno sort of posed the question. What does it mean for an infinite process to finish 200 years later? So that's Zeno. 200 years later, Archimedes says the goal of the process, I'll say something like this: the goal of the process is never reached, but it's trapped. So that's kind of his direct response to Zeno. Of course, these aren't actual quotes. These are me kind of summarizing how they were thinking. He said that infinite he pretty much said, we do not need to be scared of infinite subdivisions. We do not need to be scared of infinity, at least not in mathematics. Maybe in philosophy. We'll let you worry about that. Does not prevent that is Archimedes' response. So these are the two. Really, these guys kind of tag teamed and created the idea of calculus. And in the next video, we're going to discuss the exact idea or the official way that sort of the world has responded or made these ideas concrete. And that is through the idea of the limit. And I'll see you then.